Yeah, hello everyone. Good afternoon. Good morning here from the US. So today I'm going to be talking about work that we're doing in our group to utilize SU2 in building probabilistic aerodatabases for hypersonic vehicles. Just kind of a brief overview of the talk today. In terms of we'll go through the motivation. There's also kind of some background in terms of Gaussian process surrogate models that's relevant to the discussion, and then we can talk about kind of how we're using SU2 in a multi-fidelity modeling framework. I have some results to share, and then concluding with discussion of future work. So the motivation really is that high fidelity simulation of hypersonic vehicles is generally computationally expensive, and that's for a couple of reasons. You may have time step limitations due to high velocities. You can have complex physics, which requires physical modeling of chemical reactions, and this makes surrogate models attractive for mini query tasks such as optimization or trajectory analysis. We're also interested in this aspect of model uncertainty, particularly in hypersonic models where we have limited experimental data, and therefore, we have error bars around our simulations for both things like aerodynamic forces and moments, but also aerothermal loads like surface heating. And the result of this is that it's very useful to us to be able to quantify the epistemic uncertainty in our models when they're used in other tasks, such again as trajectory analysis or optimization, just because we're not able to fully reduce that uncertainty, which is true in all regimes, but particularly true I think in hypersonic vehicle design. And ideally, that's we want a surrogate model that incorporates the uncertainty associated with not just our sampling error, so the fact that we're using a finite set of samples to cover the domain, but also the epistemic uncertainty of the models themselves. So this is really kind of, you can think of it as the error barns around our data points. And that has motivated our use of Gaussian process regression, and particularly multi-fidelity Gaussian process regression as a surrogate model. So just briefly, we can kind of talk about Gaussian process. A Gaussian process is a stochastic process. So it's a collection of Gaussian random variables such that any finite subset are jointly distributed, and it's characterized by a mean function mu and a covariance sigma, so that you can think of the predicted value of a true scalar function f is distributed according to this this Gaussian distribution. So a really easy way to think about it is it's really kind of like a distribution over functions. So given a finite set of observations, we can write the joint distribution of a set of observations y at those points x, and get the predicted distribution using just kind of a joint Gaussian distribution. So what we're doing is, rather than assuming a particular model or functional form for our fit, our surrogate of computational results, we're modeling them as the stochastic process, which gives us more flexibility in being able to fit information. We can predict values basically by conditioning on prior observation for both the mean of our Gaussian process and as well as the covariance kernel of our Gaussian process. And the covariance is particularly useful because that's going to signify effectively the epistemic uncertainty of the resulting Gaussian process. So where we don't have very many samples, that epistemic uncertainty is going to be larger. It can actually use that as an indicator function on where to place additional samples. So throughout this work, we're using a squared exponential kernel, a radial basis function kernel is also called, and we're optimizing all of our kernel parameters through maximum likelihood estimation. And so just kind of building on those last two slides, we can also build multi-fidelity methods into Gaussian processes. And these are multi-fidelity methods in general are attractive as they permit a reduction in computational cost by using a small number of very high fidelity samples to effectively correct a larger number of low fidelity results. And the result is that typically we can get away with a large reduction in computational cost with a relatively small reduction in accuracy. And these multi-fidelity methods are particularly well suited to aerospace applications where we have large correlation between models, except maybe in a few regions where things are nonlinear, and also where there's a relatively large discrepancy between high fidelity and low fidelity model cost. So this is something that Mike Eldred at I forget if he's at Lawrence or Sandia or Los Alamos, but he's mentioned this before. And there's a framework, a very well established framework for combining information of varying fidelity levels in a single Gaussian process. It's what's called an autoregressive formulation. So the prediction z sub t at fidelity level z sub t can be seen as a basically an affine function of z sub t minus 1, so the lower fidelity Gaussian process, multiplied by a multiplicative correction and then an additive correction. And it's not super important to go into the details, I think, here, but the idea is that this is kind of the general framework we're using to combine Gaussian processes of different fidelity simulations into a single component by effectively learning what the correction is needed to take the low fidelity data and kind of bring it to the higher fidelity level. So kind of with that background out of the way, it's, I think, useful now to talk about kind of what the physical modeling, the multi-fidelity modeling framework that we're using for hypersonic vehicles with SU2. So our high fidelity simulation is performed using SU2, and specifically here we're using the perfect gas model since we're running at relatively low Mach numbers, though also we've done simulations in the past with the SU2 NEMO code on these similar geometries, incorporating thermochemical non-equilibrium effects. And then we're augmenting this with low fidelity simulation using basically what are called panel code methods. So this is local surface inclination methods like Newtonian aerodynamics, and then shock expansion methods. And we have a program called SHARP, which is basically a panel code for the wave rider geometries we'll be looking at in a second. And just to give a note, in modified Newtonian theory, which we're using for the surface pressure on the compression surface, it's very rapid, it's very easy to compute because you're just looking at what the orientation of the surface is relative to the flow vector, which is the surface inclination theta. So it's just a simple analytic computation. There's no residuals or time steps that you're having to solve. And this is very good at predicting pressure loads in high speed hypersonic flow situations. And I'll kind of show a results comparison here in a few slides to demonstrate that accuracy. But the important point is that it captures the relevant physics that we're trying to approximate. And the geometry that we're working with are boost glide vehicles, so hypersonic glide vehicles that are boosted to orbit on a rocket and then perform an unpowered glide back to Earth. And our study focuses on a parametric wave rider geometry that came out of the University of Maryland. It's a very generic wave rider. It's very kind of this very simple open source geometry, but in particular, it exhibits sufficient aerodynamic performance that it is reasonable for a gliding trajectory. For the definition of an Aerody Database, so Aerody Database is kind of a contraction of aerodynamic database. And that's going to provide a model of vehicle aerodynamic characteristics. So we're focusing on CL here, but that could also be drag coefficient, moment coefficient as a function of vehicle state. And just to kind of summarize the models that we're using that I discussed previously, SU2 is our high fidelity, and we're able to actually employ some uncertainty estimates from the literature to give us an indication of what the error bars are around our SU2 simulations. And on cost, that's on the order of CPU hours. We're running on a cluster, so the simulations themselves typically are much, in terms of time, are shorter, but in total cost, it can be on the order of 1 to 10 CPU hours. For SHARP, the kind of low fidelity code, those uncertainty estimates are a little bit more of an estimate based kind of on relative comparison and SME expertise. But the attractive feature is that the computational cost is much lower. It's around a CPU second. I just run it on my laptop, and so the what's attractive obviously is that we can run these low fidelity simulations across the whole domain for negligible computational cost. So to talk about the simulations that we're using, we looked at a particular flight condition indicative of a hypersonic glide trajectory with a free stream Mach number of 8, Reynolds number of 5 million, and we varied the angle of attack between -10 degrees and 20 degrees. That's kind of a reasonable range for what we might expect. Typically, these vehicles are going to see max leftover drag of around, something like 5 degrees. So this kind of bounds the relevant attitude profile that we might see. We can see that you get a very strong oblique shock on the compression surface below the vehicle, and you'll actually end up with an expansion fan when it's flying at positive angle of attack on the upper surface. And what's interesting about that is the properties actually in the low fidelity model are solved with a Fresnel-Meyer expansion at the leading edge, which give pretty accurate results. But it also creates kind of the suction, which leads to a thicker boundary layer on the upper surface. And so this is, again, just a simulation at 5 degrees angle of attack. And as I mentioned, we've run this at several points at kind of this alpha sweep I mentioned. And so we can kind of compare the results of our high fidelity, which is going to be SU2, so that's the red line, and then the low fidelity results, which is the sharp package, which is the green line. And again, the first key that we need to kind of combine multi-fidelity information is that the data are correlated, i.e. that we're capturing the relevant physics, even if there's bias. And for the large part, we're doing that very well in the domain, particularly at low to negative angles of attack. The Newtonian aerodynamics performs very well. We see that the discrepancy kind of grows in line with the data uncertainty of the low fidelity model as we move into higher degree, angle of attack. But the trend-wise comparison is very similar between the two. So what we're going to do with this data here, I'm going to kind of overlay the next slide after this, but it does get a little busy in terms of results, is look at building, the comparison of a multi-fidelity Gaussian process, so combining these two information together using the autoregressive formulation I mentioned previously, in comparison with just building a Gaussian process using only a subset of the high fidelity samples. So this is, again, the chart overlaid, and kind of the two main lines that we want to look at here for comparison are the orange line and then the blue line. So we've taken basically 3 samples, one at -10 degrees, 0 degrees, and 10 degrees from the high fidelity database. And we're using that to build right now a single fidelity Gaussian process with just those 3 samples, which is the orange line. This is, as we mentioned, we're trying to kind of reduce computational costs. So this is indicative of that situation. What we see is that obviously where the data is present, we get very good agreement. But then once we don't have relevant data, the orange line underpredicts the expected trend in lift at high angle of attack. Now the blue line is using the same 3 orange data points, but it's also incorporating information from the 16 low fidelity data points. So that's the green line. And the result is that it does a much better job of actually kind of capturing the trend of the data in the high angle of attack regime, so between 10 and 20 degrees, where we don't have any high fidelity samples present. And in fact, it really remains within the error bars of those high fidelity simulations. And this is the case in the absence of this high fidelity data. We're effectively utilizing the trend-wise information from low fidelity to correct the high fidelity data as best we can. And this, again, is kind of the main idea of these multi-fidelity simulations. And just to kind of summarize, using this low fidelity alone, which would be kind of the cheapest surrogate model we could do, we see an RMS error here of about 0.07 on top of the CL of that ranges from about 0.1 to 0.4. For the high fidelity information alone, it's obviously doing much better with just the 3 points, but it has lower accuracy towards the end where no data is present. And this multi-fidelity Gaussian process, which just has the lowest error of all three of those combinations, effectively, with negligibly more computational costs than the high fidelity GP alone, sees a pretty significant reduction in error. And this is all, of course, relative to the 7 high fidelity samples. So the key idea here is that really just using those low fidelity and high fidelity data, we're able to generate a very similar curve to just the 7 high fidelity samples with minimal error and significantly less computational costs. So in conclusion, we've used these multi-fidelity Gaussian processes for hypersonic vehicles using SU2 as the high fidelity model. We saw using low fidelity simulations to augment high fidelity data sets gave us a significant reduction in computational cost and accuracy. This is obviously a very simple example, so we're working to build up kind of larger databases, sweeping over a higher number of dimensions. And we're also interested in aerothermal loads prediction. So this is going to be looking at, high fidelity modeling of aerothermal phenomena, catalytic heating, et cetera. And so that's something where we're interested in exploring that further as well. Yeah, and so just to thank our grant from OSR, our computational resources from SRRC, and then obviously the SU2 community and SU2 working group, SU2 NEMO working group in particular for all the help. So that's it. Thanks everybody, and happy to answer any questions.
We have time for questions? Yes, please.
Did you try to different sampling for the ones
Yes, Jacob, the question from Giulio is, have you tried different samplings in your parameter space, and see how this would affect the results? Am I right?
Yeah, that's a very good question. As you can probably tell, the example here is a little bit contrived in that typically you'd want to sample at both ends of your domain. So not having a sample at the 20-degree mark kind of exaggerates a little bit of the difference. But that's also something we have to do here in one dimension over kind of a small sample space to get good results. But yeah, in general, the result is very much affected by sampling. Fitting a GP in general is very dependent on kind of getting a good initial sampling to get a good estimate of kernel hyperparameters. So in general, what we're doing in the higher dimensional spaces is we're using some kind of like quasi-random quasi-uniform, like a Latin hypercube type sample to make sure that we're getting a uniform sampling of all the data. And then we may adaptively refine based on the uncertainty and place additional high fidelity samples there.
Okay, thank you very much, Jacob. Let's thank our author again.